Um, yeah, this talk is, well, as the title said, it's going to be about quasi-convex subgroups at some point. But the main topic is this tool, which we're actually not so certain about what are the possible uses of this tool. But the tool is foldings of cube complexes. And let me start by going back to the first occurrence of folding, which is classical Stallings fold. So what are those? Those are tools invented by Stallings to study subgroups of free groups. And the basic idea is very simple, and this is probably why it was so prolific and fruitful. So you have your free groups presented as the rows, and you have let's say a finitely generated subgroup of this free group, which you write using the generators. So you have something. Okay, and now what you can do is you can write those words on a rose with two petals. So this is one generator, and the other one is well, I choose something quite bad for my example. So the other generator is A, C, B, C, C. Okay. And now we want to study questions. For example, what's the? We know that any subgroup of a free group is free. What is the rank of this free subgroup? So what he suggested is we want to understand really how this thing embeds into the free group. If we understand it geometrically, we'll also understand the algebraic property like rank. So as we can see, this gives us a map from this rows to this rows. But this map is not a local injective map. Okay, so suggest is fold until it is injective, locally injective. So what we have here, we have two outgoing edges labeled A, and the first thing we'll do is fold those two together. We have one edge labeled A, and then we have B going out, C, and the rest of the steps. And I think my example was quite boring because this was enough. Okay, so already, am I wrong? You should correct me if I'm wrong. This ends with a C. I think it's okay. So now this map is a local injective at each point, which translates to, if you look at the universal cover of this and the universal cover of this, the map you get is really an isometry. Okay, so the two trees, but now they're really embedded. While if you look at the first one, there is some gluing to be done in order for this to be injected. Okay, you all know this idea. Let me describe a variant of this, which is again due to Stallings. So this was in order to study the subgroup, okay, subgroup of a free group. And while doing the folds, you should notice that maybe something folds over another petal. And so the rank might reduce at some point. Okay, and this is exactly what gives us at the end the right rank of the subgroup. So my point is using those folding moves, maybe the group would change. Okay, if we start with this 2-generated free group, maybe after foldings we'll discover that it's actually cyclic. Okay. Another tool is to study actions instead of studying subgroups. So let's call them G3 foldings. So here we have our group, we fix our group, but we're interested in the actions of this group on a tree. Okay? Unlike this, where the initial group is this F2, but maybe it turns out that it's not F2, it's less than 2-gen. So here we fix G, and we let it act on a tree. And let's assume we are in the scenario where this tree maps equivalently to a different tree on which G acts. Maybe let me put the prime here. And let's assume that we understand this action better than this one, and we want to understand this action. Okay? So again, we're faced with the same problem that this map is far from being an isometry. Okay, and we want to have a process that, after finitely many steps, or I don't know, maybe infinitely many steps, brings us to a situation where we have an isometry. We want to understand this action and not the first one. Okay, and so you can do exactly the same thing. Now let's do it in the universal cover and not on the quotient, though you can describe everything on the quotient folding graph of groups. So here you have the tree T prime, and it's mapped somehow to this tree T. Okay, so what we can do here is we see, for example, so the map is, I don't know, as you imagine it to be. So this is sent to this, those two edges are sent to this edge, and something. So we see that those two edges are folded together in this process, and so we want to define this Stallings G3 foldings. What we do is we identify those two edges, and we have to do it G equivalently, otherwise we lose the G equivalence of the map. So fold two edges and extend this folding G equivalently. So what we get is another tree. So here we folded. Here you get something like this. And there is maybe another fold to be done here. Okay. So this process gives us trees on which G acts. So that's the property we want to always have. The maps are always G equivariant, and we understand this one, and we understand each one of the folds. Then maybe we have some hope of understanding the resulting tree. So this idea was used by Bestvina and Fein, for example, in what Benjamin mentioned in his talk, the accessibility over slender groups. So what they did is, so you want to study this kind of action. You have G acting on a tree with, let's say, slender edge stabilizers. And you need some more assumptions. The action should be reduced, whatever that means. And you want to bound the number of edges, of orbits of edges. So you want to bound so the number of edges in T mod. So what they did is they did a two-step it's a two-step idea. The first idea is look at the resolution. Okay, so let's assume G is finitely presented. So what Benjamin described in his talk was the resolution. You look at the presentation complex for G, you map it G equivariantly into the tree T, and then you pull back the mid edges to get walls on this presentation complex, from which you get another tree. So this is called the resolution T prime. Okay, so this is done with this resolution. You get a tree T prime, which maps G equivariantly to T. And now, as we saw in Benjamin's talk, this tree is much simpler than the original one. So, for example, the edge stabilizers here are always finitely generated, no matter what the original tree was. Here we assume slender, so maybe it's not the example, but in general, this one is much simpler. So this is one property. The other property is we have the bound. We have Dunwoodie's bound on the number of tracks, which was what Benjamin was talking about for cube complex, which I'm going to get to in a second. So here we have a bound on the number of, the size of this thing, up to parallelism. That's always an issue. And we want to understand this. And so what they do is they apply this folding machinery, and they understand how the folding what kind of folding can occur, and what they do to the number of edges. Okay, so then plus folding. Okay, but from this I want us to take the general idea of, you start with an object that you don't understand at all. You have an action of your group on some tree, and from this what you want is first to get an action on an object you have more control on, and then the second step is go back to the original complex by performing certain moves. Okay, and the moves are going to be this kind of foldings. Okay. So now let's get into what foldings are. Yes. So yeah, first of all, we need to define what are quotients of cube complexes. Okay. So note that this folding thing was very nice. We just took two edges. We identified the edges. It was very topologically very simple move. For cube complexes, we're going to get something which behaves quite differently. It's sort of more internal to the structure of the cube complex, and we're going to use poxets, so the poxet point of view of cube complexes. So let me remind or define what poxets are. So the general idea is, let X be a ket0 cube complex, and in X we can look at the hyperplanes, right, and the associated two half spaces of this thing. So let me denote by H all the half spaces of X. And now this set of the set of half spaces has two natural objects attached to it. The first is a relation, which is inclusion of half spaces. So this would be inclusion of half spaces. And the second one is a complement half space thing. So for each half space, there is the bounding hyperplane, and the other side, the complement, is another half space. So this is the complement half space. And the point is that those three things fully characterize the cube complex. So forget about the rest of the cube complex. You just remember this set, this poset on the set, and this operation on the set. You can reconstruct the cube complex out of this data. Okay, so this is the poset. So it's a poset with complementation. So this is a poset. You can define it abstractly by, okay, you need to understand what's the relation between those two operations, but maybe clear, you can imagine what those are. And the point is, posets are exactly the same as ket-zero cube complexes. Okay, so we're gonna work with this language of cube complexes, even though it's maybe a bit new and combinatorial and less geometric. And now we want to define what are quotients of ket-zero cube complexes. Okay, so here what we want to have is we have our set of half spaces. We have our poset, okay, and we have a certain relation. So this is going to be an equivalence relation on H with certain properties, of course, plus properties. And what we want to get out of this a poset structure on this. Okay, this is how we do quotients. Yes, and for this we need certain assumptions on this relation, and maybe I should do some drawing to see what are the kind of things we want out of this. So let's imagine maybe a very simple cube complex. Let me do it here. Very simple, okay? And so this has already 8 half spaces. So you see that it gets more interesting. And what we want to do is we want to identify this hyperplane with this hyperplane. So let's give them names. So let's say that this direction, this half space is H, and the other one is H star. And this is K and K star. And here we'll have T and T star and some other, I already have H.
Can you rather go smaller?
Yes, I can find. Yeah, so H star, K star, T, T star, and let's do T prime. Still too small?
Yeah.
Okay. Imagine that the letters H, T, K, and T prime are written big enough. Okay. Now let's try and fold. So what I want is the two those two hyperplanes to become one after folding. Okay. So here is the actual result I want at the end. I want to have T is not identified with anything else. It's going to be this. Have T prime. Now I have H. So it's H and H prime. And I have K. And T prime. Again, too small. Sorry. And I want to identify those two hyperplanes, and the only way possible to do it is by adding another square here. And now after adding this square, see that the hyperplanes are identified. So this is already quite new compared to to the folding of trees. When you fold trees, in the way Stallings does it, you only get trees back. There's no way.
That is a tree.
That is a tree, but now we're doing a folding that Stallings does not allow.
Okay.
Right? The folding Stallings allows is only folding two adjacent edges. And when you do that, you can just identify the edges. Here, I took two non-adjacent edges and try to fold them together. I have to add in the square. So we see that the dimension can increase. Okay, so what is the folding in terms of the equivalence relation? So we see that T and T prime are not equivalent to anything else, so they just remain their own equivalence class. But here we identified H with K star. Okay, and whenever you do this, you have to also identify their complements. So complement is identified too. Okay, and now let's try and describe what's the new pocket structure on this thing that would give us this picture. Okay, so the new pocket structure is you take two equivalence classes, and now you ask whether or not they always agree on who is inside the other. Okay, so we want to have a poset on this thing. And what we want is, we want them to agree on who is inside the other. What does it mean? So let's... So we look at the two classes, H and K, and we want to decide whether or not there is an equivalence, an inequality sign between them. So what we do is we look at all of the half spaces in those equivalence classes that are not separated by any other hyperplanes in those equivalence classes, and we see if they agree on their sign. So let me give you an example, this is also true in the usual Stalling folds. Let's say I want to do the following. I'm taking a line, okay, an infinite line, and I want to fold it like an accordion. Okay, so let me do it in a suggestive way. This is the line, okay, and I want to fold it to this. Okay, so in this case, you see that you have the hyperplanes, let's say H and H. Again, it's too small. Prime H star and K and K star, which I want to identify, and I also want to identify those and so on. So you see that I want to identify H and K and T together, right? So if I just compare what happens for H and T, I see that they actually, it's maybe a example for what I wanted. Yeah, let's add another, just another edge. It's not going to be affected, and let's call this something. P. So we see that H and P agree on their inclusion, right? H contains P. So also here I'm going to see H contains P. Okay, but notice that, for example, T does not contain P, and T is glued to H, right? Identified with H. But this is where we need this assumption that we're looking at closest possible. So I'm only comparing P to K or H. I'm not comparing it to something which is separated already by something else. Okay? And let's go back to this example. Let's see why T must cross H and K, this new hyperplane. If we try to apply this rule, we try to see if T is contained in H, for example. So we see that T is contained in H. Okay, so at least that T has to be inside H. But on the other hand, if you compare it to K, you see that that T is not. T also contains K, which is the complement of H. Okay, so you see these two contradicting inequalities, and so they must intersect. That's the idea. You get intersections when two hyperplanes cannot decide if one contains the other or not. Okay. Now let's talk about folding. So far it was about quotients. So foldings are going to be a special kind of quotient. So for foldings, we first need resolution. So let me just briefly remind you the construction of the resolution. So you have G is some finely presented groups, and let's say K is the presentation complex of or any simplified complex whose pi 1 is G. And let's assume G acts on a cube complex X. Get your cube complex. What we want to describe is a new cube complex that maps G equivalently to X and is in some ways simpler or somewhere more geometric. We can see it. So the way we do it is we look at the universal cover of K, and we map it G equivalently to X. Okay, by mapping each representative of an orbit to something and then extending it G equivalently, mapping edges to geodesics, mapping two simplices to a filling triangle inside the cube complex.
We have some assumption on the action.
So far, no assumption at all. But the problem, as we'll see, there are some pathologies in this thing. So maybe you pull back and you get a much uglier cube complex than what you started with. So, for example, you can start with the co-compact action and pull back and get something which is not co-compact, which is from someone who's used to do it for trees. It's surprising, right? If you pull back trees, you'll get a co-compact action. This is also true for square complex. I'll mention it in a second. So, yeah. So now you pull back. So this is a G equivalent map. You pull back hyperplanes to get what we call patterns or set of walls as in Daniel's talk. Okay, and they give you, by construction of Sagiv, they give you a cube complex, a new cube complex X prime. Okay, on which G acts, and this has a map from X prime to X. So G acts on X prime, this maps to X, G acts here, and this is G equivalent. Okay, so we are in exactly the same scenario as what I was trying to describe there for Stallings G3 foldings. So now it's a matter of trying to break this map down to smaller pieces which we can understand by foldings, or at least this is what we suggest. So now let's try and understand why I'm not happy with the original map. So I claim that geometrically it's a bad map, right? Like the map for trees. It's not isometric anyway. And why is it not isometric? So for example, let's even though those are cat zero spaces, most people that work with cube complexes like the combinatorial metric coming from the one skeleton, right? This is the L1 metric. Sorry. So this map x prime to x is not an L1 embedding. And what we hope is after we do foldings, which I didn't describe yet, we'll get something which is an L1 embedding. So in particular, if you understand the metric here, in the resulted folded thing, you understand this embedding in X. Okay, so why is it not an L1 embedding? The reason is simply because there are hyperplanes which are being identified even though they are not identified originally. Okay, so what could happen in this pullback is you take a hyperplane in X, you pull it back, you get more than one connected component in K tilde. Okay, and now those two things must be identified after the map. They belong to the same hyperplane. Okay, so this is exactly the thing we want to do. So so what we do is, so foldings, those are quotients that are given by identifying two adjacent as possible hyperplanes which are being identified. So let's call it F, for example. So if f of h, so now h is in x prime, is the half space of x prime, and a different half space k are being identified by f, then we want to fold them together. But there is an extra assumption that, as I said, we want them to be as adjacent as possible and not separated by another identified pair. Then look at the equivalence relation generated by identifying h and k. Of course, we have to identify the complements, and we need to do it G-equivalently if we want the group to act on the quotient. So we want GH identified to GK. And okay. So now let me try and walk you through an example. And the example is, let's start with G being Z, acting. Okay, we get to choose our representation complex for Z. Take just one circle. Okay, so acting on the line. So this is our K tilde. Okay, and and the cube complex I want this group to act on is the following finite cube complex made out of 4 squares, and the action is just rotation by pi over 2. Okay, I admit it's a weird example, but okay. So this is how Z acts. So let's say generated by A does this. Okay, and so what we have is our map from from R into here, let's say that the map we choose is the one following the perimeter of the squares. Okay. So here you have R wrapping around this thing. We pull back the hyperplanes. Okay, so we have say this is one hyperplane, another. I don't have enough colors. And that seem like the same colors, but they're not. And you pull them back. So you see this is, for example, red, and then green, yellow, red, and so on. This brown, which looks like red, but I cannot do anything about it, yellow and green, and so on. Okay, so those are the new, this is just the pullback of those hyperplanes, and we construct the cube complex that they give us, which is just putting a point between any two such things. Okay. And now we want to start folding this thing to get back to this picture. So what we do is we see, okay, for example, those two reds should be the same hyperplanes. So let's start by folding them. So you fold them together. This also means that you do it G-equivariantly. So for example, the two greens are glued together, and the two yellows and the two browns, and so on. And what is the cube complex you get is it's actually a square complex, and it's this infinite fan square complex. And so on. So you see here is, for example, the red and the green, and so on. So you see we're getting a bit closer to this picture, but it's still infinite. But now you notice that there is another identification to be done, right? This is the same as the 4-click translate of this, right? Go around this, get to the same hyperplane. So after you do this fold, you actually get the square back. So there's another fold, and you get this. So in this case, we started with a cube complex we understand. We folded it to something which is maybe much more complicated, but we ended up with the given cube complex. In this case, there is not even, it's not just isometrically embedded, it's really the cube complex. Okay. But in general, what we have is the following. And this is also the kind of theorem Bethwina and Fein used in their proof of accessibility. So you have G, let's say finely presented, though it's okay. You have X, some ket-zero cube complex on which G acts. Okay, and now let's assume that all the hyperplane stabilizers in G, so for all hyperplane, this is finely generated, and let X prime be the resolution described. Then there is a finite folding sequence that gets you from X prime to a complex which L1 embeds into X. So the folding sequence X prime folds to X1, X2, etc. till we arrive at some Xn, which now L1 embeds into X. And if I want you to take anything out of the stock, is the following notation, which I'm very proud of. as this is the symbol for L1 embedding, because this line L1 embeds in them. Okay, so forget everything else. Just remember this and use it, please.
What about stabilizers?
What?
Stabilizers.
The stabilizers of?
The action on.
So this is already L1 embeds into X. It has exactly the same, or there are no two hyperplanes which are being glued at this point from Xn to X. So it has exactly the right stabilizers as X. And let me just say that this is actually necessary, because we said that when you resolve, you get finely generated hyperplane stabilizers in the resolution. This is always true. You start with a finely presented group, you do this resolution, you get something which is finely generated hyperplane stabilizers. And this folding thing, if you only fold two of them at a time, you can only add finely many generators. Okay, so the end result here must have finely generated hyperplane stabilizers. So if you want this to end, this should have finely generated hyperplane stabilizers already at the beginning. Okay, and now let me try to describe how this can be useful to for quasi-convex subgroups. So, or undistortion in general. So you see the general way we understand those things is, let's say the group G was, let's say, some subgroup of a group that acts geometrically on X, okay, which is finely presented. And you can do this thing for this G. And then at the end, maybe you get something on which this G acts geometrically. If this is the case, then you know that this subgroup is undistorted inside the original one, because you did this process, you ended up with something on which it acts geometrically, but now it really isometrically embeds in this thing. So it's really undistorted at this point. Okay, and that's the general philosophy of the result I'm gonna talk about. So here is one of those examples. So let's say G is a surface group or a free group. Also, and and G acts on some cube complex, and I want to know whether or not this G action is undistorted, meaning the mapping G to G of X for some X. Okay, the orbit map is a quasi-isometry embedding of G into X. Okay, so what I can do this process, and if I know that the stabilizers are finely generated, then I end up with something which isometrically embeds. So the assumption is, so if the stabilizers of hyperplanes are finely generated, then I claim G is undistorted in X. And the reason is the following. So let's prove this theorem. So we already have 90% of the proof. Just need to add one more thing, or two things. When we resolve something to a surface or to the rows, we always get something which is quasi-convex. which is co-compact. Okay, so the action, so first ingredient, the action on the resolution is co-compact. Okay. The second ingredient is we have this finite folding sequence. Finite folding sequence. And the third ingredient is this co-compactness is not ruined by folding. Okay, so if you have something on which you act, let's say, co-boundedly, then also on the folded thing you will act co-boundedly. So you iterate this till you get to this point, which you act properly co-compactly, and this embeds into X. So point is foldings preserve co-boundedness. So we get the conclusion. Let me show you another variant of this thing. Maybe I should write it over this theorem because it's really the same proof works. So now instead of assuming something about G, just assume that G is finitely presented. Okay, and we'll assume something about X. Okay, so let's assume that that this X is two-dimensional. And again, the same proof works. So the only thing we have to verify is the first point, and this is what I told you that gets completely ruined after dimension 2. But if you resolve a two-dimensional complex on which you acted co-compactly, or actually any two, you will act co-compactly on the resulting thing. So let me write it here. The resolution of a two-dimensional complex is co-compact. And the reason is you look at the walls you get, and all the cubes of the resolution are visible in this picture of walls. Okay, so you do exactly what Benjamin described. You put a vertex for any connected components after you remove the walls. You connect them if they differ by a wall, and so on. You see only squares. Everything is nice, and you get a co-compact action. The problem happens when you go to dimension 3. Let me try to describe such an example of a co-compact action that resolves to a non-co-compact action. So if you have Z2, if I have Z2 acting on R2 times an interval, a very nice cube complex. So how would it act on this? So let's say the generators here are terrible. A and B. So A and B are going to act on R2 as the usual action of Z2 on R2. But what they're going to do is they're going to flip this interval. Okay. So A and B flip the interval and act like the standard action on R2. So it's worth drawing the thing, but if you do the resolution, what you might get is that this hyperplane corresponding to 0, 1 would give you another set of parallel lines in R2. So this has a universal the universal of the presentation complex we would usually choose is R2. Okay, and what we get is we get the hyperplanes of R2 in there. But this hyperplane lifts to another set of parallel lines. Okay, if you construct the cube complex out of this, you get gigantic cubes sticking out of the board, and so the action is not co-compact. But this is sort of cheating because we know that after one fold, if we identify those things, this problem is going to be gone. So this idea is what we use for the following theorem, with which I'm going to end my talk. So in this theorem, we want to talk about quasi-convex subgroups of a hyperbolic cubulated group. So GB hyperbolic cubulated, and let H be a finitely presented, no, I only need finitely generated subgroup of G. And now I'm claiming H is quasi-convex if and only if the following condition holds. If you look at hyperplane stabilizers, if it is quasi-convex, the hyperplane stabilizers are anyway quasi-convex, and the intersection of the two, meaning the stabilizers in this subgroup, are also quasi-convex, hence hyperbolic, hence finitely generated. Okay, so out of this, I'm only going to take finitely generated. Okay, so the stabilizers of hyperplanes in H are finitely generated. This is not enough. What I want is not only hyperplanes but also intersections of hyperplanes, which is still, you can do the same argument to show that if it's quasi-convex, then they're going to be finitely generated. So H is now an intersection of pairwise transverse hyperplanes in the cube complex X corresponding to G. Okay, and this, as we saw, maybe the resolution is not co-compact, but after folding, we get something which is co-compact. So it's a slightly different argument than this, but it uses folding. Okay, thank you. Wait, I have to use this. Yes.
Thank you very much. Other questions? In your theorem, you said any action is allowed, but I'm worried about actions that are not faithful.
Yeah, maybe I assumed.
I mean, if it's just a
maybe
trivial action,
the thing is, well, what we assume usually is that this has an action by a group, let's say a geometric action by a group, and this G is really a subgroup.
Oh.
So I think you only need to assume something like proper action. So maybe that's it. Thanks.
Wait. You mean faithful? Not proper. Well, proper would be enough.
Yeah, but it's too much. I mean, if you stabilize the hyperplanes are finite function, yeah, okay. Okay, one.
No, the point is you want this to be proper co-compact. I only explain why it's co-compact, right? So yeah.
That means you want it to be proper.
Yeah. I mean, otherwise, I'm not sure you can even expect a distortion, right?
So I have a question about the last term.
Yes.
So quasi-convex is like undistorted, right?
Yes, exactly.
So could you imagine that you can really have a kind of characterization when you have a quantified distortion, say quadratic, whatever?
In terms of what? Because, I mean, here you know that they're not going to be finitely generated, and you're asking at what rate you have to add generators using foldings or this kind.
Yeah.
maybe. I have no idea. It's a good question.
Last quick question.
What is the latex comment for the arrow?
What's the, sorry?
You tie it in latex, the arrow.
This you should ask Benjamin.
Okay, so we reconvene in 3 minutes.